Okay, so let's see this corollary. Actually, we have already proved this, but now we are going to see an alternate proof which uses the binomial theorem and induction. So, as usual, a is any integer and p is a prime number. Then we have to prove that the pth power of a is congruent to a modulo p. So, this is alternate proof. We are first of all going to consider the case where a is a non-negative integer. In fact, let's take the case a equal to 0 separately. In that case, obviously it's true. Clearly, this is just equal to 0 and so is also congruent to 0 mod p. Also, 1 to the power p is equal to 1 and hence it's also congruent to 1 mod p. And this becomes a basis for our induction for proving this when a is a positive integer. Assume that the statement is true for some positive integer a. Now we want to prove it for a plus 1. And we are going to consider the expansion of a plus 1 by using the binomial theorem. By the binomial theorem, the pth power of a plus 1 is a to the power p plus p choose 1. You sometimes also denote this by writing pc1. That is old notation, okay. Usually this notation is used. This is in use. This is a binomial coefficient times a to the power p minus 1 plus, let me write one more term, p choose 2. Actually, you know that we also have p choose 0 here because that is 1, we haven't written that. A to the power p minus 2 and like that it goes, and finally before we reach the last term we have this binomial coefficient and here we will have a and then plus p choose p which is 1. Okay, so we let it sit like this, and now we are going to see one fact about these binomial coefficients, the ones that we have shown here. Here also we have p choose 0 and p choose p, but we do not have anything to say about them. For these binomial coefficients though, what we want to show is that they are already positive integers, we know that. But now we are additionally claiming that they are divisible by p. Now, for any, okay, so how do you take the general binomial coefficient in this range? It's going to look like this. P choose k, where k is an integer satisfying these inequalities. So if we consider the binomial coefficient p choose k and write what it is, then we get this p times p minus 1 times p minus 2 and so on, p minus k plus 1 divided by k factorial. Okay, so that's what we get. The definition, however, if you want, you can write the definition also here. It will be p factorial divided by p minus k factorial times k factorial. It's the fact that you can write p factorial as this product times p minus k factorial, that we have this expression, because then p minus k factorial gets cancelled from the numerator and denominator and we are left with this. So from this, what do we get? Which implies, if you now multiply both sides of this equation by k factorial, you will get k factorial times p choose k is equal to this product. So you can clearly see that this is equal to p times an integer. So p divides this. Hence, p divides k factorial times p choose k. Now, since p is a prime, we know from a previous result that then p has to divide either k factorial or this one, at least one of these two. It may divide both of them also, but at least one must be divisible by p. However, k factorial is not divisible by p, since we have this. So p does not divide k factorial. And what is the reason? The reason, of course, is this. You already know that k factorial is this product 1 times 2 times 3 and so on up to k. So if p divided k factorial, it should have divided at least one of these numbers. However, all these numbers, including k, are positive integers less than p, strictly less than p, and none of them, of course, is divisible by p. And that is why p cannot divide k factorial. This again is happening because p is a prime. Okay. You can write within brackets there, note that k factorial is equal to this. That indicates why p does not divide k factorial. But then p has to divide this, which is what we were claiming there. But then p divides p choose k. This means that all these binomial coefficients that you see here are divisible by p. That is why if you now want to calculate the integer that is congruent to a plus 1 to the power p modulo p, then the contributions of these terms having these binomial coefficients will all be 0, because each one of them is congruent to 0 mod p. So we can write, hence a plus 1 to the power p is congruent to only this. When you start calculating congruence modulo p, only this term survives and this term survives. The others contribute 0. Okay, modulo P we will write afterwards, but we have other things to write. It's still not over. And now you use your induction hypothesis, which was our assumption that the claim is true for A. So A to the power P itself is congruent to A. And that's why that plus 1 is congruent to A plus 1 modulo P. But look at this congruence. This is just that statement, but with A plus 1 in place of A. The pth power of A plus 1 is congruent to A plus 1 modulo P. So by induction, this way also you can write in words. The claim is true for all positive integers A, including the case A equal to 0. We can write that the claim is true for all non-negative integers. But A may be negative also. What about that case? Next, let A be a negative integer. Then by the division algorithm, there exists integers Q and R such that A is equal to QP plus R. That means we are dividing A by P, the quotient obtained is Q and the remainder is R. And you then have to write what the remainder, what type of number it is, those inequalities, where first of all the remainder is non-negative and then it's also less than the divisor P. This part is not that important for us now, but the non-negativity of the remainder is important. And also from this equation, what do we get? We get that A minus R is divisible by P. In other words, A is congruent to R modulo P. So, A is congruent to R modulo P. Thus, by what we have proved above, that means our claim we have proved for non-negative integers. Now we can use that here. By that thing, A to the power P, since A is congruent to R, so the pth power of A is congruent to the pth power of R. But R is non-negative and we have proved the claim for non-negative integers already. So this will be congruent to R modulo P by the above proof. And R of course is again congruent to A mod P. So in this case also, where A is negative, still the pth power of A is congruent to A mod P. Now the claim has been proved entirely. Okay, so these are Fermat's theorem and its corollary. Now let us see how we can use this theorem, corollary, all these things to do some calculations quickly. Suppose we have something like this. Let me just, although it's not an example in the text, but still let me just write example. Show that it's just a discussion in the text. Show that 5 to the power 38 is congruent to 4 modulo 11. Okay, so how can we, of course, we won't be, we are not going to calculate 5 to the power 38 exactly. That may be very large. So what we are going to do is we will use this corollary. We know that 5 to, note that the modulus 11 is a prime. So we are in a position to use, actually not the corollary also, but Fermat's little theorem itself. That's because 11 does not divide 5. So that condition is there. And that's why 5 to the power p minus 1, that means 11 minus 1, 10, is congruent to 1 modulo 11. Can write the congruence sign here itself. Alright, now we can of course write 5 to the power 38 as this. So 5 to the power 38, first of all, this is 5 to the power 10 cube times 5 to the power 8. 30 plus 8 is 38. So this is congruent to 1 cube times 5 to the power 8. That means we now have 5 to the power 8. Now how can we further reduce 5 to the power 8? Let's see what is 5 square. 5 square is 25. Now 25, when you divide that by 11, it looks like this, right? So you get 22 plus 3. That is how you have the use of the division algorithm here. And that's why this becomes congruent to 3 mod 11. So you can now use this fact. You can write the 8th power as the 4th power of the square, of course. So this will be congruent to 3 to the power 4 mod 11. Because we are going on writing these things and we still have more to write. So we do not yet write mod 11. So this of course can be calculated quite easily, and this equals 81. Now if you divide 81 by 11, what do you get? Of course you can go till the 7 times 11. So you get 77, and that gives you what? Plus 4. Yeah. And that's why 81 is congruent to 4 mod 11. So that's how 5 to the power 38 is congruent to 4 mod 11. This is rough work. Okay, so that's how, without going through the hassle of actually calculating this number, we were able to show that this is congruent to 4 mod 11. Or in another language, if you divide this, whatever number it ultimately becomes, somewhat a large number, when you divide that number by 11, the remainder is 4. Why do I say remainder? Because 4 is non-negative and less than 11, that's why. Okay, now we are going to make an observation about this, about the above corollary. What does the corollary say? Let me write it here. It says that if P is prime, then a to the power P is congruent to A mod P for all P. Look at this statement. This statement is an implication. No? Its structure is if then. That means there is a hypothesis and there is a conclusion. The hypothesis is that P is a prime number, and the conclusion is that this congruence is true for all integers A, without any restriction, for all integers, for all A. What is the contrapositive of this implication? Let me actually write this as an implication. P is prime implies this for all A. What is the contrapositive of this implication? The contrapositive, if your implication is like this, the P statement P implies statement Q, contrapositive by definition is negation of Q implies negation of P. And you know from elementary logic that a statement, an implication and its contrapositive are logically equivalent. If any one of them is true, the other one must also be true. And that is why this statement is equivalent to its contrapositive, which is, what will be the negation of this statement? The statement is this for all. Universal quantifier is there. Okay, so to form its negation, you just write the negation of this and change for all by for some. A to the power P is incongruent to A mod P for some A. That's how you negate a statement which has logical quantifiers. You negate the actual part of the statement, then you change the quantifier by that other one. If you have for all, you change that to for some. If for some, then for all. Implies the negation of this statement, that is P is not prime. This may be useful. It says that if you are not sure about a positive integer P, whether it is prime or not, prime or composite, if somehow you find an integer A for which you have this, an incongruence or non-congruence, then P has to be composite, it cannot be prime. And we are now going to use this to prove that the number 117 is not prime. Consider the integer 117. You will also quickly realize that although this is a way of showing that some integer is composite, but why it's really not practical after all. The number 117 is quite small, so you can maybe just try to divided by something. That way you may get a prime factor quickly, showing that it is indeed composite. But this is also another way of doing it. So what shall we choose for A? The author has taken A equal to 2. That means we now have to calculate 2 to the power 117. If we can somehow show that that is not congruent to 2 modulo 117, then the above logic will tell us that 117 is not prime. So let's see what we can do. The author has noted that this is 2 to the power 7 to the power 16 times 2 to the power 5, because 7 times 16 plus 5 is 117. So the rules of exponents have been used here. Now what can we do with these smaller powers of 2, 2 to the power 7 and 2 to the power 5? That's what we will next see. Two to the power 7 is not, it's not very difficult to calculate. What will it be? 128. Okay, so $128, and our number is 117. So what shall we get if we subtract? We are getting 11. That's because I'm saying we have to subtract, because 2 times 117 exceeds 128. So that is why this is congruent to 11 mod 170. So we can now simplify to some extent. Hence 2 to the power 7. But let's not go for the entire number now itself. Let's just take this part. This is congruent to 11 to the power 16. This is also a very large number. Okay. Now, what about, we have got 11 to the power 16. That's quite a large quantity. So that can be, that can be simplified, of course. Because we have powers of a power of 2 here, so you can write that as 11 square to the power 8. So that way you will get 121 to the power 8. All right. Now 121 you can do 121 plus. So if you are dividing by 117, okay, so 117 is less than, of course. Yeah, I was thinking it's greater than 121. Why? So this is 4. So that's why here you have a little simplification. 4 to the power 8. That means 2 to the power 16. Okay. Now 2 to the power 16, of course, again can be written like this. 2 to the power 7 times, we can of course take squares, so that way we will get 2 to the power 14, and we are left with what? 14 plus 2 is 16. That means 4. And we already know that 2 to the power 7 is congruent to 11. So this is congruent to 11 square times 4. That is 121 times 4. But what about 121? 121 itself is congruent to 4 mod 117. So 4 times 4, that is congruent to 16 mod 117. But we are not there quite yet, because we have this 2 to the power 5. Hence, to the power 117 is equal to I hope I have done everything correctly. So this is equal to the 16th power of 2 to the power 7 times 2 to the power 5, and this thing is congruent to 16 times 2 to the power 5 is, well, let me just keep it like this, because this is also a power of 2, no? That means this is 9. So again we can bring 2 to the power 7. Modulo 117. So finally we have been able to see that this large number is congruent to 44 mod 117. Now since obviously 44 is not congruent to 2 mod 117, we have 2 to the power 117 not congruent to 2 mod 117. This is not congruent to 2 because the difference is 42. That of course is not divisible by 117. 42 is positive and less than 117. How can it be divisible? Hence, 117 is not prime. And in fact, if one goes looking for a factor, it's very easy to find. Do you remember the criterion for divisibility by 3? The sum of the digits should be divisible by 3. What is that sum? 1 plus 1, 2, 2 plus 7, 9. Okay, so it's divisible by 3. That way you can find a prime factor. And one can check that 117 is 13 times 9. So obviously it's composite, and you may be thinking why we have to go through all this. It's just a demonstration that demonstration of that observation. Okay, nothing more than that. Moreover, this method is really not feasible because it relies on the existence of some A for which, perhaps I should not write P here, N, for which we have this. Now, there is nothing that is telling you how to find such an A, if an A really exists. Maybe because of something else you suspect that a given number n is composite, it should be composite, then you just try all possible values of a. So do you see how impractical that is? A may really be very large. So that's why this is not a practical method, but it does show that if one goes like this, one will not get congruent, one will not get congruence, one will get incongruence. So let me just stop the video here itself. After this also there are many more things. Here in this related to Fermat's theorem itself, there are many more things that we will discuss in the next number theory video. So that's just it. See you in the next upload. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.